Let's start.
Okay, sorry. So this clicker works?
Yeah.
Okay.
I hope. Right.
Okay, good. Yeah, as an introduction, my name is Masanobu, so please call me Masa. And I'm a postdoc researcher in Hokkaido University. And since Hokkaido is a northern part of Japan, and now it is under 0°C, so I'm happy to be here. Good. So before starting the content, I have two things to say. The first, this work is based on the discussion with Katsuhiko, who was my supervisor when I was in doctoral course. And moreover, this work is financially supported by JSPS. Good. So let's cut the chase. So before explaining the detailed stuff, let me explain our contributions in this presentation. There are two contributions, namely, the first contribution is to provide the star semantics for the logic code EMP, and logic EMP is the expansion of intuitionistic propositional logic by a special negation called empirical negation. So this is the first contribution. And the second contribution is by providing the star semantics, we reveal the relationship between EMP and other logics having star semantics. So these two are our contributions. And to put it more concretely, this is our main theorem. We show all of the following four items equivalent. And the Kripke semantics mentioned in the first item was already proposed. And the Hubel system mentioned in the second item was also already proposed. However, the Hubel system mentioned in the third item is a new one, as far as we know. And the fourth item says that A is valid in some classes of star frames. So by providing the equivalence of these four items, we newly provide the star semantics for the logic EMP. So this is our main theorem. And with respect to the relationships with the other logics having the star semantics, these logics are known as logics having the star semantics. And these are the relationships between such a kind of logics. And what we show is EMP is placed here. So this is a second contribution of ourselves. So let us start the content. Before jumping into the technical detail, since many of you do not know about the logic EMP, let me explain the background of EMP. The logic EMP was proposed by Michael D., the second guy, following Michael Dammett's argument, philosophical argument. And Michael Dammett's argument is starting by considering this kind of sentence, like a Goldbacher's conjecture is not solved. As many of you know, Michael Dammett is known as the advocate of intuitionistic logic. However, Dammett says that if we interpret this negation by the intuitionistic propositional logic, it fails to capture the intended meaning of this sentence. Because if we use intuitionistic negation to interpret this sentence, what is said is, if Goldbacher's conjecture is solved, then it contradicts. However, this is different from what is intended in this sentence. What is intended in this sentence is there is no proof or warrant to establish the Goldbacher's conjecture in this stage. So this is an argument proposed by Michael Dammett. And based on this argument, Mike D proposed the logic by giving the Kripke semantics. And after that, Sato Niki, this third guy, proposed the Bev semantics. And there is also an algebraic semantics proposed by Niki and Omori. And because of the limitation of time, we only talk about the Kripke semantics in this presentation. Good, so let us jump into the technical stuff. So let me define the syntax of this talk. The syntax consists of propositional variables, conjunction, disjunction, and implication and negation. And conjunction, disjunction, and implication are treated as the intuitionistic ones. However, this negation is a negation which is different from intuitionistic one. So this negation is distinguished from intuitionistic negation. And although bottom is not included in this syntax, we can define bottom as this formula. Good. So let us jump into the Kripke semantics. The notion of Kripke model is defined as a tuple of these 4 elements. And W is a non-empty set of states. And G is a distinguished element equipped with a model. And the accessibility relation is defined to be a partial order on W. And V is a variation function that is a function from the set of propositional variables to power set of W, satisfying this persistency condition. In the following, when I say a variation function, it is assumed that this condition is satisfied. And one character of this notion of Kripke model is the notion of distinguished element. And these give the satisfaction relations for connectives. We are omitting the satisfaction relations for disjunction because you can infer from the second clause. And as I said, propositional variable, conjunction, disjunction, and implication are treated as the intuitionistic ones. And on the top of that, we add the satisfaction condition for negation. And this is a satisfaction relation for negation. And what is said here is negation A holds in the state W if and only if A does not hold in the state G. And G is a distinguished element in the model. So, and it is said that informal interpretation of this negation can be provided by regarding G as a present evidential situation or something. So, for example, negation A holds if and only if there is no warrant in the present evidential situation or something. So this is an informal interpretation. So let us see an example. So this is a Kripke model for intuitionistic logic. Note that there is a reflexive rule for each state, but we are omitting it just for the simplicity. And in this model, since P does not hold in the state G, negation P holds everywhere. We only see this distinguished space. So negation P holds everywhere. And the notion of validity is defined as this in the Kripke semantics. A is valid if and only if for any Kripke model, A is true in the state G. So when we give the notion of validity, we only stick to the distinguished state. And let us proceed to the proof theoretic stuff. The Hubel system for the logic was already proposed by Nikki and Omori. And it is based upon the Hubel system for positive fragment of intuitionistic propositional calculus. And it is obtained by adding these 3 actions and 1 rule on the top of the calculus. And the first one is one of the De Morgan laws. And the second one is law of excluded middle. And the third one is what I like to call as quasi principles of explosion. And the final one is law of contraposition as a rule form. Yeah. So this is a Hubel system. And this fact was already established. So A is a theorem in the Hubel system, if and only if A is valid in the Kripke semantics. So soundness and completeness holds. So this is an established fact, already established fact. So let us see our main theorem again. What we have seen is the equivalence between 1 and 2 holds, and it was already shown by Nikki and Omori. Good, so let us proceed to the sorry, and in the following, we will deal with 3 and 4. And although the logic EMP itself is philosophically motivated and interesting as it is, but as a research of logic, an interesting question is what the relationship between EMP and other logics is. And this kind of questions are pursued in these papers. There is no time to explain a lot of stuff in these papers. However, let me tell you one interesting character of the logic. So yeah, this is an interesting character of the logic EMP. If we define the notion of classical syntax and the intuitionistic syntax in this way, then the logic EMP is a conservative extension of both classical and positive intuitionistic propositional logic. So this is an interesting property of the logic EMP. And in the following, we pursue this question. However, the logics treated in this presentation are not treated in these papers. Good. So let us see our contribution again. First, we provide the star semantics for the logic EMP, which is different from the Kripke semantics. And we review the relationship between EMP and other logics having the star semantics. Good. So let us proceed to the star semantics. The notion of a frame is defined as a tuple of these 3 elements. And W and accessibility relation are the same as the Kripke model. And star is a function from W to W satisfying this condition. And this condition is needed in order for the logic to be closed under uniform substitution. Good. And the notion of a star model is defined as you can expect. So these 3 elements should construct a star frame, and V should be a variation function. And one important point is there is no notion of the distinguished element in this model. Good. And the satisfaction relations for conjunction, disjunction, and implication are the same as the intuitionistic ones. And this is the satisfaction relation for negation. And what this satisfaction condition is saying is negation A holds in the state W if and only if A does not hold in the state W star, as is already described by the first presentation of this session. And this negation is known as a negation in Australian plan of relevant logics. Yeah. Good. So let us see an example again. So let us deal with this Kripke model again. On the top of this Kripke model, we add a star function, and this dotted line describes the situation of the star function. For example, since G star is G itself, and P does not hold in the state G, negation P holds in the state G. And in a similar way, since W star is V and P does not hold in the state V, negation P holds in the state W. And in the same way, since V star is W and P holds in the state W, negation P does not hold in the state V. So this is an example. And let us proceed to a notion of validity. We define the notion of validity in a frame and in a class of frames. So this is the notion of validity in a frame. A is valid in a frame if and only if for any variation function B and any arbitrary chosen state A is true in that state. Since there is no notion of the distinguished element, we consider arbitrary chosen state in this notion of validity. And this is a notion of validity in a class of frames. And in the following, let FO be the class of all star frames. And let us proceed to the proof theoretic stuff. Let us deal with the system called HN star. And it is obtained by adding these 4 axioms and 1 rule on the top of the positive fragment of intuitionistic propositional calculus. N1 and NR are the same as H, as in HEMP, and N2 is another De Morgan rule, and N3 says bottom implies everything, namely, and N4 says it is not the case that top implies bottom. So this is a Hilbert system called HN star. Then we can get this equivalence. So A is seldom in this Hilbert system if and only if A is buried in the class of all star frames. So this fact was already shown. And based on this logic, we can consider many extensions of N star where the classical logic is the strongest. And N star DNE is an extension of N star by double negation elimination. And it corresponds to the class of all star frames satisfying this condition. And N star DNI is an expansion of N star by double negation introduction. And it corresponds to the class of all star frames satisfying this condition. And if you add both double negation introduction and elimination, then we reach the logic called Ni star, which is also called height. And N star cont is an extension of N star by a law of contradiction, and it corresponds to the class of all star frames satisfying this condition. And if you add both of double negation elimination and law of contradiction, we reach classical logic. And one interesting observation is this condition is obtained by exchanging the left-hand side and right-hand side of this condition. So the natural question to ask is, what kind of thing happens when you exchange the left-hand side and the right-hand side of the condition for N star cont? So this is an interesting question. So we deal with this question. So let F star PR be the class of all star frames satisfying this condition. And this is a converse of the condition for N star cont, this condition. And as far as we know, this is a newly established theorem. We can get this fact. For any star frame F, this equivalence holds. So F satisfies this condition if and only if PU and negation P is buried in that frame. So in the term of model logic, PU and negation P defines the class of all star frames satisfying this condition. And based on this fact, let us deal with the system obtained by adding row of excluded middle as a scheme on the top of Hn star. And let us call the system Hn star LEM. And as you can expect, we can get this proposition. A is a theorem in the Hilbert system if and only if A is buried in the class of all star frames, satisfying the condition. So let us see our main theorem again. We have seen that the equivalence between 1 and 2 was already established. And we have seen that the equivalence between 3 and 4 holds. So what should be established is the bridge 1 and 2 on the one hand, and 3 and 4 on the other hand. So this is what we have to do next. And this can be done by purely syntactic way. So we can get this equivalence. A is a theorem in an extension of N star by row of excluded middle, if and only if A is a theorem in the Hilbert system for EMP. And this can be shown in a purely syntactic way. So we successfully bridge 1, 2, and 3, and 4 by showing the equivalence between two Hilbert systems. So we reach our main theorem. So let me explain the place of EMP. And EMP is placed here. And there is no time to explain, but if you add row of excluded middle on the top of N star, then you can derive double negation elimination. So EMP is stronger than N star the NE. And as I said, if you add both of double negation elimination and law of contradiction, then we reach classical logic. But if you add law of extruded middle and double negation introduction, then we can also reach the classical logic. Yeah, and this logic corresponds to this condition. And with respect to the class of planes, in N star cont and EMP, W star is equal to W star star. So no matter how many stars are added, it stays in the same state. And in Ni star or height, W is equal to W star star. So it is sometimes says involutive model. And in classical logic, everything collapses. And with respect to the notion of, with respect to a property of negation, these 5 logics is an Occam negation. Now, Occam negation is a negation satisfying all of the De Morgan's laws with respect to conjunction and disjunction. And a negation in Ni star is a De Morgan negation, which is an Occam negation satisfying also double negation introduction and elimination. And the classical negation is also negation, and also negation is that the Morgan negation also satisfies law of contradiction and law of excluded middle. So finally, let me mention very briefly about the previous research. So this is a paper written by Mike D and Hitoshi Omori. And in this paper, star semantics is mentioned here. And they wrote, in this case, the star function maps every word to a single word, namely the base vowel G. The base vowel is a distinguished element in this, in my presentation. So with respect to the Kripke semantics, this definition of the star function is very straightforward and natural. But what we have reviewed is there is no need of the notion of the distinguished state. So in other words, more concretely, we can derive this corollary from our main theorem. There is no formula in the sense of modal logic defining the class of all star frames satisfying this constant function property. So we can get this corollary. So let me finish. This is the final slide. So let me finish my presentation by briefly mentioning the notion of the semantic consequence relation. Insofar, we only dealt with Theorem and Barrett formulas, but the notion of semantic consequence relation of EMP was already defined by D and Omori in the framework of Kripke semantics as this. A is a semantic consequence of gamma if and only if for any Kripke model, if all the formulas in gamma hold in the state G, then A also holds in the state G. So in the definition of the semantic consequence relation, they also stick to the notion of the distinguished element, the truth preservation of the distinguished element. However, there is no notion of the distinguished element in the star semantics. It is an interesting question how this semantic consequence relation can be defined in the star frame. And we revealed that this semantic consequence relation can be defined in the star semantics as this. For any star frame satisfying the condition and arbitrary chosen state, if all the formulas in gamma hold in the state W star, then A also holds in the W star. So we do not have to appeal to the distinguished state. We have to, instead of it, we have to appeal to the notion of star. So in other words, we can define this consequence relation as a local consequence relation in terms of the states with star. Yeah. So this is the final slide. So thank you for your attention.